Assalamualaikum and good day everyone. So I hope everyone in good health and excited to learn further. Okay, so now we're going to continue on the um, synchronous receiver coherent detector. Okay, let me enable the presentation box. Okay. So today we're going to learn about synchronous FSK receiver frequency shifting, or also known as a coherent detector. So if you see, this is our VFSK, okay, the frequency shifting voltage, okay, signals, okay, and this is a mixer, okay. So this VSK will be multiplied, will be mixed with cos omega C plus theta omega here, okay, and then we'll go through the summer, okay, amplitude. The same signal, frequency shifting, will go through here, but will be mixed with cos omega C minus theta omega. And then it will go through here to the summer amplifier. So this the products of this will be minus by the product of this due to these operations. Okay, then it will undergo LPF, where the higher frequency will be removed. Okay, so in the end we will either have EC over 2, which is basically our bit 1, or EC minus negative EC over 2. Okay, so we can have either this or this, means 1 O 1 O 1 O. Okay, depends on what is the bit designation. So if it's EC over 2, it is a bit 1. Okay, so this is a probability of error, which is bit of error, the probability of finding error bit in over the bit, the total over the bits. Okay, so here is over the bits, total bit. Okay, so you have here is 1 over 2. This one is error function. Okay, this one we have learned before. Okay, this one is energy per bit, and this one is your noise power spectrum. Okay, so if it's double-sided, okay, it will be like this and not over 2. Okay, so ERC, ERFC here is referred to error function, just now I told just now. Okay, so if the received signal, let's say our received signal here, let's say is VFSK EC cos omega C plus. Okay, you see here plus. Okay, means this can be designed as our bit 1. Okay, depend on the question. Okay, let's say this one is can be our bit 1. Okay, frequency shifting, just like analogy to frequency modulation. But here we're going to have two different frequency. The lower frequency usually will present the bit 0, and the higher frequency will represent the bit 1. For example, this one omega C plus theta omega, so it will be more, right? The frequency will be more, this one will be less. So this one is bit 0 lah. Okay, so let's say this one is bit 0. So you can have either bit 1 or bit 0. After that, it's going to be mixed. Okay, so if the input, okay, if the input A is here, okay, you're going to have input B here, okay, which is this one. If your input here is C, you're going to have input from the amplifier D, which is this one. Okay, so we go to the next example. This cut. Okay, let me close first the example so that we learn properly. Okay, so this one will be cut. Okay, here. Okay, we learn from this first. Okay, so you should see here FSK signal in example 5.1 is fed to synchronous receiver. Okay, means the signal that is produced by the generator. Now we're going to receive it at our receiver. So calculate the new BER and compare with that of BER which use a synchronous receiver. So if you see here, okay, if you see here the question example 5.1 and asynchronous, okay, asynchronous, because example 5.2 will be using 5.1 information. Okay, so let me revisit first example 5.1. So asynchronous FSK system is modulated by digital signal and operate at 10 MHz. The frequency deviation is 850 Hz and bit rate is 110 bits per second. The peak to peak carrier is this. Okay, and noise power for spectrum density is this. Okay, so calculate the BER for system. So we end up having EB. Okay, what is EB just now is energy per bit. Okay, so we get the energy per bit, which is this. Okay, let me, okay, I don't know why I couldn't okay, so never mind, 4.55 times 10 to power of 93 millijoule, and our BER, okay, for bit error rate is 5.74 times 10 to power of -6. So now we can see, we go to example 5.2. FSK signal in example 5.1, okay, is fed to synchronous receiver. Calculate the new, okay, the new BER and compare with that of BER which use asynchronous receiver, means before this, okay, because this one just now is asynchronous receiver. An example that we obtain from the answer is for the asynchronous system for example 5.1. Now 5.2 is this question. Okay, so let me change the screen. Stop sharing. And then I'm sharing this screen right now, screen 1. Okay. Okay, so where is my touch screen? Okay, so we receive from our example 5.1, our asynchronous, okay, our asynchronous receiver, okay, we receive the value of EB equals to 5.1 5.55 times millijoule, okay, and then we have B probability of error bit, okay, small e equivalent approximate to bit error rate, okay, and we get it 5.74 times 10 to power of -6. Also can be said that we're going to see 6 error bit over 10,000 over 10 to the power of 6. Okay, so next example 5.2 is that, okay, this FSK signal is in example 5.1. Okay, the FSK signal there is fed now to the synchronous receiver, means just now is error bit and probability of error for synchronous, for asynchronous receiver, this one. Okay, now we are doing for the same FSK signal that is fed in the example 5.1. Now it will go to the synchronous receiver. So calculate the new BER, and also and we need to compare. Okay, so okay, this one is from example 5.1. Okay, so also from 5.1, okay, and O equals to, this one is from example 5.1, and O equals to 2 times 10 to the power of -4 volts, okay, volts square over hertz. Okay, so FSK signal in example 5.1 is fed to the synchronous receiver. So this one is asynchronous. Now we are doing for synchronous receiver. Okay, for example 5.2, the same signal, FSK signal, but now it's going to the synchronous receiver. Okay. So taking the same equation, so we have bit error rate, PE equals to, okay, go to our slide number 18, okay, so it is a half error function, okay, square root 0.5 EB energy per bit over our N naught, okay, over our N naught. And this one is, this question is for double-sided, okay. But the same is formation can be used, okay, can be used. So 0.5 EB. We just write the general equation first, okay, over N naught, okay, N naught. So half, using the information that you will get, okay, from the example 5.1, so the EB is 4.55 millijoule, okay, 4.55 millijoule, so 0.5 EB, the one we get from example 5.1. Now we are using them this again. So here will be, I just put A, so that too easy for space. So is A, and then the next N naught, okay, N naught, which is I put here as B, okay. So it will be put here, will be used here, okay. And when you're solving, okay, when we're solving, so we will find out that half, okay, of the error function, you calculate this, you will get 3.37, okay. This 3.37, okay, sorry, so this 3.37, you refer to the error function table. So what did you get for error function for 3.33 receiver? Okay, so it is around 1.88. I don't have error function. Sorry, I don't have the appendix with me. So turn out when you refer to the error function table, you get 1.88 times 10 to the power of negative 6. Then you divide by 2, you get 0.94 times 10 to the power of negative 6. Okay. Then is equivalent to, if we summarize, this one is equivalent to 1, right? 1 over 10 to the power of 6. Okay. So if you see it, if you compare between a synchronous receiver, okay, here, let me using a different color. For asynchronous receiver, you can see that the probability of error or bit error rate is, you're going to find 6 error bit over 10,006, okay. But for this, for the synchronous receiver, you only find 1 error bit over 10 to the power of 6 bits, okay. So if you see this, it means that we can see from here, we can say that synchronous receiver have better probability error rate, okay, have better bit error rate, because if you see, it only contain 1 error bit over 10 to the power of 6 bits, okay, compared to the asynchronous receiver, okay. So I take this one and I put to the slide, okay? But never mind, this is recorded. You can always refer again, right? I put either way in my slides, and you can put in your slide as well. This slide. Okay. So the next, we go to, okay. So let we see. Let we now try to visualize this one. Okay. Let's say we have let's say we have input VFSK equals to EC cos omega C plus theta omega. Okay. And after that, it's going to be mixed, okay, because it's parallel here, divided. It's going to mix with this, and it's going to be mixed with this. However, this one is product minus with product of this one, okay. So let me see. I just do general so that you can see the picture, okay. I take this first. Okay. Then I remove the screen. Wait for a while. Please bear with me. I'm sorry. Okay, because it's tricky, but normal, because not all of our screen is touch screen. Okay, so how I'm going to bring this back there? Okay, I put here. Then this one, new screen. Concept. And this one we put here. Okay. So this is our system coherent detector or synchronous FSK receiver. So imagine that our VFSK, the one that we receive, okay, I use different color so they're easier. So I use maybe black first, so that then we will differentiate that. Let's say we have signal VFSK. The signal that we receive here, VFSK, equals to, okay, with VFSK with of course with time. Let's say the signal that we receive is EEC cos omega C plus delta omega. Okay, so, okay. So let me remove this first. It's kind of disturbing, right? Okay. So if you see time is I'm recording this is around 1:40 a.m. Okay. So but it's kind of no noise because it's late night, but hopefully you bear with me. I hope I'm going to deliver it properly, inshallah. I try my best. Okay, so this is VFSK, which is the one that we receive here. Okay, let's say I will receive here. So if this is plus, okay, means this one will be higher frequency, right? So this one will be bit 1. Okay, let's say if the omega C minus theta omega, if it's minus, so it will be 0, okay, if it's minus, okay, this, okay. But let's say we actually receive, okay, let's say we receive bit 1, so this one is of course plus, okay, plus omega 2, okay. Next, it will be multiply, okay, we use different color now. It will be multiply with this one and also this one, okay, mix, okay. Now the amplifier outputs, okay, here, okay, means at VD, you can use now different color, VD plus VD, okay, VDT, the output from the amplifier. So VDT is equals to, the first is EC cos omega C plus delta omega T. Okay, and then multiply with the above. Okay, with the above, because it's going to multiply with both, right? So first it will multiply EC cos omega C T, omega C omega T, our VSK multiply with this first. So cos omega C plus delta omega T. Okay, then it will be minus. Okay, it will be minus because the next one is will be minus. You see here, because there is minus. So the next is minus. Okay, you see here minus. Then we continue below because no space. Next is EC, the same signal because it's passed through here now. EC cos omega C plus omega delta omega T. Now times with cos omega C minus delta omega T. Okay, if you imagine, okay, this one is cos A. Okay, you will do your trigonometry, right? Cos omega C plus delta omega T. Let's say we can put it as a cos A. Okay, and then the next is cos omega C minus. I found this on the web. You put it in the next discourse. Check it out. Sorry, my phone is interrupting me. So you see cos omega C minus now is equals to cos B. This one is, you just try to make it look simpler. Okay, so you're going to solve it using trigo. So this one will be cos A, cos B, and this one will be cos A, cos, sorry, this one will be cos A, and below will be cos A, cos B, right? Okay. When you solve, you're going to have the answer. Okay, you, because I have no space, you solve this. Okay, you expand, then VDT with, if your VFSK is actually bit 1, if this one, so you're going to have EC. Okay, after you do the expansion of your triangle, you have EC minus 2 EC over 2 cos 2 delta omega T plus cos 2 omega CT minus cos, okay, 2 omega C plus delta omega T. Okay, so then this is your VDT, which is, if you see, if I were to mark, okay, this VDT here is the one you receive here, okay, then it will pass through low pass filter. So when it passes through low pass filter, all of the higher frequency will be removed. So this one, all of this will be removed because it's a high frequency. So the outcome you have, which is here VMT, okay, in the end you will only have VMT equals to EC over 2. Okay, and EC, then this EC over 2 is your bit 1. Okay, So if you see here, you can try with the next one. You can try with the bit 0, which is VFSK. Okay, you try yourself at home. T equals to EC, okay, VFSK bit 0 now, EC cos omega C minus delta omega T. Okay, so if you put this into here, okay, you end up we receive at the VMT as negative EC over 2. So negative EC over 2 is your bit 0. Okay, so now let me change the screen. Stop sharing. Then we share the other screen. Continue here. Okay, so that's why here you say that LPF will allow either EC or omega C, which will represent the output digital signals. Okay, so you try this at home so that you can you don't just accept this figure, but you can try you try it, then you will appreciate, okay, the operation. Okay, and you can relate if you do it yourself, rather than just looking. Okay, so you practice. So this one we already went through just now. Okay, so the next is phase shift keying. What does it mean by phase shift keying? Means we're going to change phase. So there will be changes in the phase of signals. Okay, let me activate the presentation mode so that easy for us. Okay, so that is more meaningful if we activate the presentation mode. Okay, so this is phase shift key, means there will be changes in phase. So if you see, this is your carrier. Okay, this is your carrier, and this is your basically your information signal in terms of bit signals. Okay, so if you see here, this is carrier, which is omega C, and this is your information signal where you have omega omega M, 3 omega M, and 5 omega M. Depends on the number of the harmonics. Okay, okay, continue because I'm still using it. Okay, so now for the phase shift key, the phase of the carrier is set to 0 or 180. Okay, 0 degree or 180 depending on the digital signal. So PSSK signal can be represented by this general equation: VPSK is cos omega CT plus phi t. Okay, so if the bit is 0, okay, sorry, if the phi is 0, if the phi is 0, mean it will be bit 1, and if the phi is 1 at 0, it will be a bit 0. Okay, so you go to here, VPSKT, if you have phi equals to 0 inside, okay, you will end up EC cos omega CT. You will have like, this is a 1. Okay, means you're going to have inversion, inversion, but in terms of phase inversion, but in terms of positive. Okay, empty positive here. And then the next, if you have VPSK, okay, if you have 1 at 0, okay, you input here 1 at 0, you're going to have, if you put 1 at 0 here, okay, you're going to have negative amplitude EC cos omega CT. So there will be inversion in terms of amplitude. Okay, so means changes in phase, changes in phase. So this will be 0. Okay, but this one is changes in the positive, and this one will be changes in the negative amplitude. Okay, so if you see, this is your the output of your PSK. So if you see, this is your carrier modulated with bit 1 of your information signal. So if you see here, And then, sorry, if you see this one is 1 and changing to the next one, which is 0. Okay. So if you see 0 here is actually inverted by negative. Okay, there is phase inversion, but invert negative. Okay, so you see here, rather than should be continue because there is change of bit, it inverse, but the inverse below because of the negative EC here. Okay, and the next one, the next changes is from 0 to bit 1. So because it is bit 1, so you're going to have the changes in the inversion phase shift. You have the changes in EC cos omega CT. So this is where the signal should continue down, but it is inverse. Okay, phase inversion and positive because EC cos. Okay, that's why it's here. Okay, the next one, let's say continue with the same bit, so nothing inversion happen. Then we have the next one, which is the change of bit. So if you see, this one is 1 changed to 0. So because we have negative EC cos, okay, it will be inverse to phase inversion and negative. Okay, phase inversion of 180 degree. Okay, this one from 0 to 1, you're going to have phase shift of 0 degree. Okay, but then the amplitude is 1. You see here. Okay, I hope they're clear. I hope you can see it. From 1 change to 0. So you're going to have negative EC cos omega CT. So it's invert. Okay, it's phase shift by 180. Then the answer will be like negative amplitude because you see here is negative. Okay, next from 0 to 1, you're going to have phase inversion 0. Okay, you're going to have phase shift 0, and it is positive lah in the amplitude. So this one like this. Okay, so next BPSK, which is the results of your carrier times your VMT. So just now, right, our VMT, because this chapter 5 is our information signal is bit signal, right? And VCT is our carrier, okay, which is higher frequency than our information. Taking Fourier series of bipolar signal, okay, bipolar signal is that we have, as I told you last time, right, what is bipolar, right? Okay, bipolar means we're going to have a positive and negative value. Okay, bipolar. Taking bipolar signal, so our VMT is equals to 4 over pi cos omega t minus 1 over 3 3 omega t and 5 omega t. This one is until 5 harmonics. Okay, until 5 omega m t. So this one, how we get it? Please refer to signal and system subject. Okay, where we learn about this one. Okay, rectangular. This one you already learned in signal system. Otherwise, you will not take this subject because you have to pass signal system, only then you can take this subject. So we just carry forward the knowledge from signal system to here. Okay, so you know how to get this, right? Okay, from the signal and system. This one is a Fourier series. Okay, bipolar means we're going to have positive and negative values. Okay, and we have VCT equals to EC cos omega CT. This one is our carrier just now. Okay, this one is our carrier, which is, of course, what we know, the frequency is much higher than our omega m. Therefore, the result would be for VPSK, we're going to have the multiplication results. You're going to have EC cos omega CT 4 over pi and so on, and we simplify, you're going to have 2 over pi EC cos omega C plus minus omega m and until 5. So if the question want until 5 harmonics, so means it's until 5 harmonics only. And if you see here, there is plus and minus, right? So your answer can be cos omega, cos plus omega m minus half cos omega c plus 3 omega m, or you can have cos omega c minus omega m, omega c minus 3 omega m, and so on. Okay, depends. Next, so for the bandwidth, okay, for the bandwidth of PSK, it is equals to FB, where FB is equals to 2FM. Okay, so this bandwidth in PSK is just the same as the bandwidth in amplitude shift gain. Okay, and so the bandwidth is ASK is equivalent to the bandwidth in PSK. Okay, if we see from the spectrum, PSK spectrum, so this is your spectrum. So you can see this one from bawah tekan mean suppressed carrier. Okay, this one is suppressed carrier, means we don't have suppressed, we don't have carrier here, means the carrier is suppressed, suppressed carrier. Okay, from bawah tekan is suppressed carrier, so it's here suppressed. Then this is the bandwidth of your PSK bandwidth, and here is the lower frequency, and this one is the higher frequency. So if you see, this one is Fm minus 1 over T1. Okay, and this one is Fm plus 1 over T1. Okay, so this is your bandwidth. Okay, this one is your bandwidth for your PSK. So this is what we study in the previous slide just now. So if 1 change to 0, okay, it's supposed to be continue, right? But because there is change in bit, so we see what will happen next. So 1 change to 0, so it's going to have phase shift of 1 at 0 degree. So that's why when cos omega c t minus 1 at 0, so your EC will be negative, right? So that's why it's here. Okay, then the next one is change, then the next one is change from bit 0 to bit 1. In change to 0 to bit 1, the phase shift is 0, so your EC cos omega c plus 0, you're going to have EC cos omega ct, means EC positive, so that's why you continue is positive. Okay, and so on. Okay, next is the PSK. If we want to generate, okay, if you want to generate our so what, how long I progress now? Okay, 38 minutes. Okay, next is if we want to generate our PSK signals. Okay, so how to generate PSK signal is that we empty our information signal, okay, which is in terms of the bits, okay, and go to low pass filter, okay, to remove any higher frequency, and then will be mixed with our carrier, which is higher frequency, right? Then our FM, then mix, then you will get your VPSK. Okay, so this is this is just block diagram. So this one is the more specific lah block. Okay, so if you see here, this one is your PSK transmitter. Okay, if you see here, if you see here, there is two input, okay, to the double balance modulator. One is carrier. Okay, if you see here, this one is carrier sine wave. Okay, carrier sine wave, which is this input to here. Okay, and the next one is your information signals. Okay, you see here is none return to 0. M waveform unipolar means only have one sign. Okay, like positive 5 to 0. Okay, and then going to here, then we will change it from unipolar to bipolar converter. So for example, from 5 0, it will become, for example, positive 2.5 and negative 2.5. Okay, because it's convert, right? Convert, just convert from unipolar and having bipolar. Okay, then if we goes to this as a modulation input, so this one is actually our information signal or our modulating signal, and they will be mixed here, right? For this, then we're going to have the output here where it actually is here. Okay, and on the receiver sides, okay, on the receiver side, we have the PSK input signal, for example, of course, like this one, VPSK. Now we're going to input it here because it's receiver. Then it will go to the PSK demodulator. So we're going to demodulate it. And low pass filter, I think you know already because you want to remove the higher frequency. Okay, because our we just want the information. Information is lower in frequency. Then it will go to voltage comparator. Okay, voltage comparator, it will compare the positive and negative. Then it will go to the differential bit decoder. Then you're going to have NRZL data output. So this one is your finally your VMT. Okay, so I mean it will be processed until to receive your VMT, your information signal. Okay, in the receiver. Okay, um PSK receiver, phase shifting receiver, PSK demodulator must use. You see here, PSK demodulator must use coherent detector. Advantage of PSK are immune to noise. Yes, this one we already discussed. If you attend my class, okay, and because I'm not sure whether I inform this in class, because we have mix right now, recorded and also live class. Okay, but I mentioned either way in one of the platform. So advantage of PSK is immune to noise and the same bandwidth with SSK multi-level. Okay, so what is multi-level? Later you will learn in uh, the subsequent subtopic. Okay. The probability of error in the receiver of PSK is PE equals to half error function EB over N naught, and EB is equals to EC square T over 2. Okay, so using multiplier, okay, using multiplier to generate your VMT, sorry, to retrieve back, not to generate because it is receiver. Okay, I'm sorry. Now is what time? Now is 2:06 a.m. Okay, so using multiplier VPSK, then it will be mixed with your carrier. Okay, this one is at receiver side. So it is either EC cos omega CT or negative EC cos omega CT. Okay, the the carrier. Okay, and then after that, okay, mix. It will be mixed. Sorry, this one is either this one is here. Okay, I want to check first. This is the following. Okay. So if you see here, okay, this is your VPSK. Okay, this is your inputs. Okay, this is your generated VPSK signal. So this one, okay, this basically is the one that you're going to have at the input. Okay, so let me screenshot first so that you able to see. Okay, let me take first. Okay, then we go to the next slide. Next. Okay, let me change something so that you can see it carefully. So that you can see it's directly because it's coming from the previous slide, but in the next slide it's suddenly not there. So we go for, let me do some changes first. Okay, here, then I push here. Okay, I think now it's a bit clear. Wait for a while because I'm doing some adjustment. Okay, now we go to the previous slide. Because you're going to see, okay. Now you see I put it here, okay? So if you see, then I take from the previous slide. So this is VPSK, okay? VPSK 2 omega C cos omega C plus minus omega M and so on. So this is your VPSK, okay? And this one, okay, I am sorry just now, with error, sorry for that. So this one is this, okay, your carrier, okay, your carrier. Then mix together, and then you're going to have this. What is this? Now tell me, is it high pass filter or low pass filter? Okay, so I think you should know, right? Okay, we go through in the class. So what filter is this? Is it high pass filter or is it low pass filter? Okay, which one? Okay, then here VPSK, this is the one that you in from the previous class I took it, and at the receiver it will be mixed with either EC cos omega CT or an EC cos omega CT. Then go to this low pass filter or high pass filter. Okay, which one to get your PMT? So this calculate the probability of error. For example, 5.1 means the same information 5.1 using PSK and compare the bit error rate with synchronous and asynchronous FSK. So just now, in example 5.2, we already calculate the bit error rate for synchronous receiver. Okay, for example 5.2. In 5.1, we do it for the asynchronous FSK. Okay, so now we want to calculate the probability of error for example 5.1. Okay, I just open the the cover, and we just directly discuss it. So this is what coming that we saw from the example 5.1. So you get the EB, okay, energy per bit, 4.55 times 10 to the power 93 joule, or 4.55 millijoule. And N naught equals to 2 times 10 to the power of negative 4. This one is from example 5.2. Okay. uh, then we, from example 5.1, we have the bit error rate, okay, or property of error, that it is 5.7 times 10 to the power of negative 6. Then from example 5.2, we solve it, we're going to have bit error rate or probability of error is 0.94 times 10 to the power of -6. Okay, then from the table, okay, the same thing, but for the formula of QPSK, for PSK, previous, here this one, okay, the same EB and not, okay. Next, with EB is equals EC square, you see here, EC square times T over 2, okay, times T over 2. So you see half error function equals to 4.55 times 10 to the power of -3 over 2 times 10 to the power of -4. Okay, the same information, for example 5.1, then you get the half of error function 4.77. Then referring to the table, okay, you refer to error function table. So error function 4.77 is approximately equal to 1.52 times 10 to the power of -1. So it's half over, then we need to time it with half now. So that's why you have with times 2 here. Then you get the 7.6 times 10 to the power of -2. So if we change, okay, so that we can easily see it clearly. So means we're going to have 7.6 error bit. Means we have, if we run, we have 8 error bit. Okay, for 7.6 run, you have 8 bit over 10 times 10 to the power of 12 bits. Okay, so if you see this number is bigger, means you only get, okay, you only see 8-bit error, okay, which is around of 7.8 over 10 to the power of -12 bits compared to synchronous and asynchronous FSK. Okay, so that's why we can say that based on this calculation, we can say that B error rate, right? Okay, B error rate for our PSK is much smaller than bit error rate in synchronous and asynchronous FSK. So in terms, so based on this, PSK is better. Okay, is better in terms of, this is one of the way to prove lah. Let's say you get the question right, prove. Okay, then sometimes maybe calculate first and then you're going to prove, you're going to make a conclusion based on your answers. Okay, so this one you can see, right, uh, obviously PSK have better error bit, better bit error rate, because you only get 8 bit over 10 times 12, 10 times 12 bits available. This one you get, you have, for synchronous you have 1 bit error bit over 10 to the power of 6 bits. This one for asynchronous, 6 over 10 to the power of 6 at 6 error bit over time over 10 to the power of 6. So as asynchronous is the worst one, because you have much higher bit error rate. Okay, so now we go for the summary. Summary of how long this is, sorry. Okay, so maybe just another 7 minutes. So this is the summary of digital modulations. Okay, sorry. So this is your message signal, which is in terms of uh, bit signals 101011, and the results when we do amplitude shifting, the amplitude 1 and the by a bit signal means in ASK. So for bit 1, after modulated, modulate with the carrier. Okay, so bit 1 will be present, will be 1, 0 will be no pulse, no like on off, right, on and off, and 1 we have a signals, and we're going to have get the ASK signals, and then after that this will be 0. Okay, so 0 is 0 at all, mean nothing. And then we have 1, which is actually AC cos omega CT. So there is sine wave for the bit 1, and 0 didn't have. So for the FSK, basically the bit 1 is will be represented when modulated. We're going to have when bit 1 modulated with the carrier, we're going to have higher frequency compared to this, compared to when 0 is as a modulating that time with our carrier. So we're going to have lower frequency to represent our 0. So here, if you see here, based on this example, bit 0, okay, 0 is AC cos omega C1t, and 1 is AC cos omega C2. So we can see based on this, 1 is actually omega C2 is much higher than omega C1, okay, and this one is your 1, and this one is your 0. The next is phase shifting, okay, phase shifting. So for 0, you're going to have AC cos omega CT, okay, shift of 0 in, I'm sorry, wait, let me, okay, so that we, I don't want confuse, I don't want the confuse, okay. So we use the previous example, okay, just, okay, use the previous so that you will not get confused, okay. For bit 1, bit, okay, we just consistent this one 0 first, so we discuss about 0 first. If 0, okay, 0 0, it will be negative EC cos, oh my god, okay, EC cos omega C T, okay. So the next, if we have 1, okay, 1 will be EC cos omega CT, so positive one, okay. So this one, AC, EC is just the same thing, just different labeling. So if you see, from 1 change to 0, okay, from 1 change to 0, so it will have a phase shift of 180 degree, which resulted in this negative. So that's why you're going to have the next one, negative. And after that, it's continue until the next changes, bit 1. In B1 is the phase shift 0. So phase shift 0, when we talk about phase shift is this one, okay, phase shift 0, then it result into EC cos omega CT. So that's why you have EC here, you have phase shift and positive, blah blah blah. And then the next one change from 1 to 0, okay, for it will be phase shift of 180, and it will result into negative EC cos omega CT. So that's why you have negative here, okay, and so on. So this is pretty much the comparison, okay, the comparison between ASK and FSK and PSK. So So this pretty much we already covered in the previous slides. Okay. Now this just is a compilation. Okay. So for the SK, the advantage is bandwidth efficiency. However, it has more noise, more disturbed by noise. Okay, because it's amplitude, right? Uh, just like energy, this one you can energy with the for easy relation. You can energy with AM, FM, and PM lah. Okay, so for FSK, less noise and larger bandwidth, and for PSK, the bandwidth is similar to our ASK. Okay, however, it having less noise than ASK. Okay, like what we covered just now, right? The bandwidth for PSK is equal to ASK lah. However, compared to noise, PSK still have less noise problem compared to ASK. So the calculation for the bandwidth, okay, for the bandwidth, ASK is 2 FM. Okay, so if we calculate until 3 harmonics, so it will be 2 times 3 FM. Okay, because 3 harmonics, so it will be 6 FM. If until 5 harmonic, will be 2 times 5 FM. So it will be 10 FM lah. So for FSK, we need to add, okay? We need to add the same like FSK. However, we need to add 2 delta F. Okay? This is for FSK. For PSK, the same as your ASK, because what I see just now, we covered before and also to here, bandwidth is similar. That's why the bandwidth for PSK is the same as bandwidth calculation of PSK is just the same as ASK. For probability of error in ASK is half error function EB over 4 naught N naught. And for FSK, we have synchronous and asynchronous, right? For asynchronous, it's half epsilon negative EB over 2 N naught. For the synchronous, it will be half 0.5 EV over N naught. For PSK, the PE or bit error rate is half error function EB over N naught square root. Okay. So with that, we're going to stop here and we will continue our lecture, next lecture with multi-level shift keying. Okay. Thank you very much. Have a nice day. Assalamualaikum and have a good day.